Hello, Mr. Ryan, are you right? Okay, you know the power of 2, right? Yeah. So can you give me some integer which is power of 2?
16.
16? More.
Ryan said 4.
Okay, 4, yeah.
Obviously you didn't hear.
Yeah, okay. So basically the...
32, 8. 64.
Yeah, this goes on.
28.
256,
Okay.
112,000.
2.
Yeah. What's the smallest power of 2?
2.
1.
1, yes. Why? Why is 1? 2 to the power of...
Because 2 divided by 2 is 1.
2 to the power of 0. Okay. Do you still remember this?
Why is there no 2 to the power minus 1?
That's very good. We're talking about the positive integer, okay? So I will talk about the negative power, okay? Like 2 to the power of 0. A to the power of b when a is not equal to 0, okay? This is very important. When a is not equal to 0, a to the power of 0 is 1. Any number to the power of 0 is 1. A million to the power of 0 is
1.
minus 2 to the power of 0.
1.
Are you sure? Okay, let me repeat. 1, yes, I was just saying that any non-zero number to the power of 0 is 1, okay?
Then what is 0 to the power of 0?
That's a very good question. It's mathematically not defined. Okay, you can let me know why it's not defined, okay? It is not defined.
You
0,
don't
very
know.
special. I don't know, to be honest, I don't know. I have to look it up, but it's very hard to explain. Just remember, a to not equal 0. When we talk about a to the power of b, as long as a not equal to 0, a to the power of 0 equals 1. This is a could be any number except 0. Okay? So look, 2 equals 2 to the power of 1, 4 equals 2 to the power of 2, a equals 2 to the power of 3. Okay? 1024 equals 2 to the power of... We talk about this very special number.
2 to the power of 10?
Yes. Okay. Yeah, if you are a software engineer, you recognize this number because this is much widely used. And every 24th of October is the day for software engineer. Okay? Actually, we created this day.
Like
October.
There's like 1,024 gigabyte.
Yeah, we talk about like 1 gigabyte, 1 terabyte. The relation is 2 to the power of 10. Okay?
Yeah, and it's like...
So on that day,
it's one of like...
yeah,
It's like employee birthdays on the 24th of October.
Okay. Yes. Okay, so if you're on that day, you need to send me some small gifts. Right, and you're saying 2 to the power of minus 1. Okay? What's that? That equals 2 to the power of 1. 1 over that. So basically, a to the power of minus b equals a to the power of b, 1 over it. Okay? So this is 0.5. So 2 to the power of minus 2. 2 to the power of minus 2 equals 1 over 2 to the power of 2 equals 0.25. Does it make sense? Okay, so a little bit math knowledge here. So we are given a positive number n. We are given a positive number n. N is bigger or equal than 0, okay? Let's non-negative number, non-negative integer. N is a non-negative integer. N bigger or equal than 0. At one operation, you can add or subtract a power of 2. So you can, at one operation, you can n plus a or n minus a, where a is power of 2. So a is power of 2 here, okay? So at one operation, you can do this. N plus a or n minus a. A is one of these numbers, power of 2. So we want to find out the minimum number of operations to bring this number n to 0. And you can do this operation as many times as possible, okay? So it means that we can get to 0. The slowest way would be to decrement 1 n times, like 100. You can decrement 1 until you get to 0, because 1 is power of 0. Okay, but certainly 100 is not 100 times, right? It's not the minimum, because what you can do? You can subtract 64, right? And that remains 36, alright? And you can subtract 16, that remains 20. You can subtract 16 again, that remains 4. And you can subtract 4, just a few times. Okay? Or 100, what you can do is you can plus 16, make it 116. And then you plus 4, make it 120. And you plus 8 to make it 128. And you subtract 128 to make it 0. Does it make sense? And we want to find out the minimum number of operations in order to bring this number into 0. Let's take a look at an example like 5. How many steps we need to bring this number down to 0?
2.
Okay, so how?
Subtract 1. Subtract 4.
Well done. Okay, how about 7?
Plus 1. Subtract 8.
Well done, you got that. That's the question. Okay. So any idea how can we do it? Any idea?
Brute force.
How can we brute force? How can we? So I mean, I give you a number.
I just
Yeah, from these two numbers, if I give you 5, why you say minus 1 minus? So why I give you 7, why you say plus 1? I mean, I want to understand what you're thinking and how can we apply it to
This
computer. Common sense?
Yeah, just common sense.
Okay, but I mean, this number is quite small, so you can just look at it and then it's very straightforward. But if I'm saying that 116, so it's not very obvious.
Yeah.
You
Plus 16 minus 4 minus 128. Plus 16
yeah.
minus 4 minus 128.
Okay, might be correct. Okay, so what are we doing
I
here?
think.
What are we doing here? Can you summarize your solution? So what are you looking for? So how do we know you go left or right? Go left meaning the subtract, go right is
looking
subtract.
for a number which is the power of 2. So you can just subtract the power of 2 and then just you get back to 0.
Yeah, but when do you add?
So you want to go to a power of 2, so you can
But there's 2 power 2 on the left or on the right. Which
yeah,
way?
I know.
Yeah.
But is that you can subtract or
Yeah.
add
Mm-hmm.
another power of 2 to get that power of 2, and then you can subtract the power of 2 to get 0.
Okay, so look here, right? This is
Yeah,
the number,
yeah.
right?
You need to add or subtract the power of 2 to get another power of 2, so you can subtract.
Goes on, right? So let's say we have a number here. Okay.
Is that 12?
Okay, let's say 13, okay? So left or right?
You go
Right. Left.
because
Right.
because it's an odd number, but so I think you need to go you need to do 2 steps, at least 2 to get to a power of 2. For example,
Yeah.
you can do -1 plus 4 minus 16. No, or plus 4 minus 1
Okay.
and then minus 16.
Okay, so let's forget about the details.
It doesn't
Okay, so
really matter.
if you get here or get here, how many steps then? If you get to here or here, how many steps?
So to the left is
No.
5.
For example, if you're at this point, right? Suppose you can come this way or this way, but okay, forget about how you get to this point or this point. What I'm saying is that if you get to this point, how many more steps? If you get to this point, how many more steps?
If you go to
Is
the
it-
right,
if you go to the right-
One. Yes, one. Okay,
yeah,
so
that's what I'm saying. I was saying that before you go to
Yeah.
power of 2.
okay, our target is to reach this point and that point.
Yeah, I
It doesn't
know,
matter.
I know.
It's one more step, right? But the cost to move here to here, right? We know this distance. Here, this distance is 5. Here, distance is 3. Okay, 13, 8. This is distance is 5. There is a distance 3. Okay, so which one is shorter? If I want to move, okay, so now there are 5 here. I want to move here to here. This is 5 units. I want to move here to here. This is 3 units. Which one is shorter?
The 3 units.
3 units. If we say Fn is to bring this n to 0. So here this bit is F5. Here this bit is F3. So we just need to compare to the shortest one. Does it make sense? But can we just say, okay, use the F3? Do we need to check the F5 here?
No.
You say always the 3 units is always the quicker way to get to the no?
Fine, yes.
You're like falling in between, right? Okay, so we worry about this. Okay, so first of all, we need to implement this. We can compare, right? We can compare the nearest the power of 2. There are 2, one on the left, one on the right. This is 8. Okay, so the next one would be, we know, right? It's times 2. Or we use the power of 2, so we can do this log 2. Log 2 13 equals 3 point something, right? 3 point something. Log 2, base 2, log function. Are you right?
The toilet.
Yeah, sure. You know the log function, yeah? What is log function? Log AB equals C. What can we get? A to the power of C equals B. A to the power of C equals B, so we can write it this way. Log A, B, C. Okay? So log 2, 13 means that 2 to the power of what is smaller or equal than 13. If we're looking for the integer, what number should we put here? So 2 to the power of that is smaller or equal than 13. The biggest number is, we put the 3, right? Because 2 to the power of 3 is 8. 2 to the power of 4 is 16. So this something is a number between 3. This is, let's say this is A, right? So this A is between the 3 and 4. So we know this, we can find this A, and B equals A plus 1, right? And then we can just calculate this bit. Because from this point, Fn, to reach to Fa, this point 2 to the power of A, right? From N to A, 2 to the power of A, or from N to 2 to the power of A plus 1. Okay? So once we reach 2 to the power of A or 2 to the power of A plus 1, we just need one more step. So the distance between N to N minus 2 to the power of A, the number of steps is this one. The number of steps of reaching the right hand side is 2 to the power of A plus 1 minus N. Right? And we just need to compare these two, which one is shorter. Define Fn. If n equal 0, return
0.
obviously return 0. Okay, so how do we check if an integer is power of 2? We talked about this a long time ago, right? How do we check if a positive number is a power of 2? There are a couple of ways. How do we check if an integer is power of 2? Is 129 a power of 2?
No.
Is 128 a power of 2?
Yeah. 1 is the power of 2. The rest are even numbers, and if it's no number, then it's
Not, right? But 6 is not power of 2.
yeah.
Okay, so
I'm not saying
Okay.
ooh.
Okay, then given a number, so how do we know it's a power of 2?
You just divide by 2 until it's 0.
Yeah. Divide by 2. That's very good. So we keep dividing until it reaches 1, right? If it's not reaching 1, then it's not power of 2. If it's some way becomes the odd number, it's not power of 2. Or the opposite. We can multiply 2. So let's say 129 is not power of 2. So we can 1, 2, 4, 8, 16, 32 until we reach 128, or we go past 128, okay? 1 is 1, right? 0, 0, 0, 0, 0. This is binary for 1. 2 is 0, 0, 0, 0, 1, 0. This is 2. 4 is 0, 0, 0, 1, 0, 0. Okay, 0, 0, 1, 0, 0, 0. This is A. You see? You notice the pattern. This is binary. Do you notice the pattern here? This is decimal. 1, 2, 4, A. This is binary. So what do we get here? Can you see something here? 16, 0, 1, 0, 0, 0, 0. 32, what's the binary? 1, 0, 0, 0, 0, 0. Looking at the binary, what can we find for power of 2 numbers?
1 followed by 0.
That's why there's only one single one, right? There's only one single one. We talk about this. So if in binary, if there's only single one, then it's power of 2. So we can do this. If we check, obviously it has to be positive, n bigger than 0, right? And n n minus 1. If it's equal 0, then it's power of 2. Look, this is power of 2, right? 16 is the power of 2, n. So in minus 1, it subtract 1 in binary, it becomes 0, 0, 1, 1, 1, 1. Okay, this is n minus 1. N is 0, 1, 0, 0, 0, 0. Okay, so if you do the binary n, 0 and 1 is 0. It become all zeros. Okay, so we use these to check if the number is a power of 2 integer. Okay, so I'm opening the door so you can listen as well. Okay, let me continue writing this. Okay. So, okay, look. If n, and because we're given a non-negative integers, right? So if it's not 0, then here it's positive. So if n and n minus 1 equals 0. If it's power of 2, then we return, if it's power of 2, then we return how many steps?
1.
Well done, excellent. Okay, 1 step. Okay, now, okay, so look, I'm going to write this, okay? This is the key thing today. And I'm going to put the other solutions in the next lesson. This problem has quite a lot of solutions. I think this problem is very good because it involves the mathematics and programming and computer science, right? And dynamic programming, recursion, and you can do it in binary search, simple math, the bit. This problem is very good. So if we understand this problem better, then we learn a lot, right? Okay. So we want to find the closest power of 2. So let's say the closest power of 2 here is 2 to the power of a. And here will be 2 to the power of a plus 1, right? This a thing. So how do we get this a? A, we can use the math log function, log2, math.log2 function. Okay. So a equals math log2 n, but we need to convert it to integer. Okay, so math.log2 we can import math. Okay, we can say import math, the package, or we can say from math import log2, and we given this n, and it returns a number which is log2. I mean this log is not an integer, we need to convert it to integer. Okay, we need to convert it to integer, and we can use the in function or the floor function. Right, remember this floor function. Floor 3.5 is 3. Ceiling 3.5 is 4. Okay? Just imagine, the number. Floor is looking for the biggest integer, no more than current number. The ceiling is looking for the smallest integer, bigger than the current number.
It's an integer. What if it is an integer?
Well done. Yeah, that's a common case. Floor 3 equals 3. Ceiling 3 equals 3. Okay? Just Excel. This is floor. Look, it's very look, it's very vividly, right? You see? This is looking for floor, this is looking for ceiling. Yeah? Floor, ceiling, floor, ceiling.
Very vivid, not vividly.
Thank you. Okay? So we got this A. The number of step of moving to 2 to the power of A is F. We're calling the recursion, I'm calling it f. Fn minus 1 shift to the left a position. This is basically the same thing as 2 to the power of a, right? Look, binary, right? This is binary, yeah? 1 shift 1 position to the left, it becomes 2. Shift another position, it becomes 4. Okay, so the n minus 1 shift a position is basically, this is n, right? This is a, so it's basically the distance here. This is na. This is the distance, n minus 2 to the power of a. Okay, and then we want to find out the number of steps of bringing this to 0. And similarly, nb equals f. F will be this one, right? So it's 1 shift a plus 1, yeah, and minus n. Okay, so it's basically this bit, right? This bit is, okay, so it's 2 to the power of a plus 1 minus n, right? This distance. This distance is n minus 2 to the power of a. And we want to calculate the distance. Okay, and the result is just the minimum of these, right? Na and b, whichever is the smaller, mean. This is brute force. Here, so far it's brute force. Basically, what's brute force? I mean, I'm at this point n. There are only two choices. I can go left or I can go right, right? brute force with some greedy, right? Because we want to go to the nearest power of 2, right? The nearest to the power of 2, there are only two choices. The one on the left, the one on the right. But to me, I don't know which one I should go. That's fine. Ask the computer to try. NA and B. Right? This is NA steps to go if we choose to the left one.
Yeah,
go
but
to
if like, for example, you have like 160, you would go down because you can go minus 32 is 128.
160.
Yeah, you go down. No, 160. 60.
160. Yeah, you go down, right?
Yeah. To 128.
128. What's the nearest?
256.
256. Yeah, because here there's large distance.
No, but it's not just that, it's just that you can also go minus 32. And 32 is a power of 2.
Yeah, of course, yes.
Yeah, that's what I'm saying.
Ah, okay.
Unlike, for example, 211, yeah.
Okay. Yeah, I get your point. Okay, so coming back to this, right? There are two ways, and we can try. We don't know yet. We can try both ways and to see which one is smaller, right? And here recursion, right? Because look, the distance here, and we need to call the function again recursions to find out the number of steps to bring this bit to 0. To actually is from n to the cost from n to 2 to the power a, and n to 2 to the power of 2a plus 1, and whichever is smaller. This is brute force. If we put the cache here, right? Dynamic programming, top-down dynamic programming, remember here? Yeah. So actually, here we are trying both ways, right? But the greedy approach is just to pick the smaller one. So whichever is smaller here, right? And then we call the function once. So whichever is smaller. Mean, if we don't call the f function here, so we just put f mean n a and b. Whichever is smaller.
Yeah.
That's greedy. How can we prove it's correct? So basically we're saying that if this is shorter, right? Look, 160, right? Come to 200, the next one number is 256. The previous number is 128. Here, this 32, right? Here, that will be 96. So 32 is smaller than 96. So it's a no-brainer. We just go for the shorter one. We don't check this at all. Okay, obviously this is quicker, right? Okay, so this is the solution. We put a cache that becomes top-down dynamic programming, okay? And we can implement this within the loop. I'm going to talk about the while loop next lesson just to give us a better understanding, okay? Because there's a lot of content to cover, and we can also solve this using the dynamic programming. Bottom up. Actually, look, without the cache, Ryan, that's your brute force. I'm here, n. I can go to the left, I can go to the right to find the nearest power of 2. I don't know which one I should pick, and just try both. Okay, this is brute force. But if I'm putting the cache, then this suddenly become a dynamic programming equation, which is top-down. Okay, because look, if I want to solve fn, I need to solve a smaller n. Right?
Yeah.
There are two ways, and I put a cache. If we don't put a cache, then there's some number, f some number could be calculated over and over again. The time complexity will be exponential. Okay, and we also talk about another optimization, which is to pick whatever is smaller, right? Whatever is smaller. If the left is distance to the nearest power of 2 is smaller, then we just pick this one. If the right is smaller, we just pick that one, right?
Yeah.
We also talk about how to check the power of 2, right? In binary form. Math function log2 returns the floating number, and we need to use the in or float to get the integer part. So basically here is 2 to the power of a. The right power of 2 is 2 to the power of a plus 1, and n is in the middle. We use the distance, we calculate distance, which is na and b, and we decide where to go. Okay. So the time complexity for this one is O log n. We're reducing this n, right? We're reducing this n. N minus this is smaller. Every time we reduce it to log 2, right? So every time here, this is smaller, is in a scale of log 2. Okay? Space complexity here using the recursion, I think this is similar, log 2, O log 2. Okay, what have you learned today?
We power 2.
Okay, so can you just explain to me what's the problem and then how do we solve it, and that's it.
So the problem is that we've been given a number and we trying to use addition and subtraction to get it down to 0 by only subtracting or adding numbers which are the power of 2.
Mhm.
And the solution, is that find the two closest power of 2 near it, and then you try to get there because
Mhm.
the nearest one, you go to that one. Yeah, for example, 211 is 256 and 128. This one is close, so you go to that.
Yeah.
This is 45, and this is 83.
And then 45, then we can call this function f45 again.
Yeah.
Yeah.
But sometimes it doesn't matter. For example, 193. It
Yeah.
doesn't matter where you go because 128 and 256. You can go to the this one has a larger gap than this one, but you can go here because you can subtract 64,
Yeah.
which is 129, and then subtract 1 and then subtract 128, so that's 3. But it's also the same for this because you can plus 64, which is 257, and then you subtract 1 and then you subtract 250.
Well, Adam, how did you come up with this number? It's so quick. So you just have that in your mind.
Yeah.
Okay, good. Yeah. Okay, so why this approach works? Because adding and subtracting the power of 2 is equivalent, the same cost. Okay? Yeah, it's equivalent, the same cost. So that's why we can use this approach to bring down. Like, you see this distance, right? And we can use this distance to narrow down, to call a recursion function fn to solve a smaller problem. Next lesson, we're going to talk about transforming this recursion, right? Recursion into the while loop, into the iterative approach. And then the next lesson, we're going to talk about some tricky solution, which is based on the binary. That's it for today. Bye-bye.
Bye.
Bye.